Okay, our next discussion of probability involves what are called binomial random variables. A binomial random variable is a variable that can only take on two possible values. So for example, if you have a coin, you could flip a coin and you could get either a head or a tail. Those would be the two possible values. Now, even with things like rolling a die, you can define those as having two possible results or outcomes. You could roll a die and get less than 3, or you could roll a die and get greater than or equal to 3. So we're going to take a look at this idea of binomial variables and talk about the probability distribution of such variables. We'll also take a look at how to use IL to calculate probabilities from a binomial distribution. And we're going to see some examples of problems for which using a binomial distribution gives you a solution. Okay, so what is a binomial random variable? Well, a binomial random variable is a variable where we differentiate between success and non-success or failure. And we simply count the number of successes in a given sorry, I highlighted the wrong thing there. We count the number of successes out of some number of trials. So if we had a coin, we might flip the coin 10 times, and if we count head as a success, then we could count the number of heads, and that's the number of successes out of 10 flips. Each of these trials has to be independent and identical. This would be true of a coin. Each time we flip a coin, the current coin flip doesn't have any dependency on the previous coin flips. And since we're using a coin for all these flips, the results is going to be identical for each flip. As I said, there are only two possible outcomes. That's what defines this thing as a binomial variable. And we're going to call one kind of outcome success and the other one failure. So the probability of success we'll call P, and that remains fixed from one test to the next test. Since there are only two possible outcomes, success and failure, failure is the complement of success, and we call its probability Q, which, because it's a complement, we know that's going to be 1 minus P, okay? So, we're doing n trials, and in n trials, we get x successes. The probability of that occurring, the probability of getting x successes out of n trials, here we're kind of mixing our capital letters and lowercase letters, is given by this mathematical formula. This is called n choose x times the probability of success to the x power, the probability of success to the number of successes we got, times the probability of failure to the n minus x power. Okay, we're not going to, this is the formula, period. We're not going to require you to know how to apply this particular formula. We're going to just use IL to compute these probabilities. Now, I can't resist giving you a little more information about the meaning of what's called n choose x. The formula for that, if you wanted to compute it out by hand, is n factorial divided by x factorial times n minus x factorial. And what it is the number of possible combinations yielding X successes in N trials. All right. And for example, let's suppose that we flip a coin 4 times. So we're doing 4 trials. And let's suppose that this is an unfair coin. The probability of getting a head, which is how we're going to define success, is 0.8. Therefore, the probability of failure is 1 minus 0.8 is 0.2. And X here is the number of heads that we get. Our question is, what is the probability that X, the number of heads that we get, the number of successes that we get, is equal to 3? Well, if you imagine flipping a coin 4 times, then the possible outcomes that we would get include things like head, 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 tail, head, head, tail, head, 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 tail, tail. Here I have jotted down the possibilities of heads versus tails if we flip a coin 4 times. You can see that there are 16 possible outcomes, and only 4 of those possible outcomes have 3 heads. That is, we have 3 successes in these 4 ways. We've got head, 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 tail, head, head, tail, head, head, tail, head, head, and finally tail, head, head, head. Now, the probability of any one of these 16 things occurring has to be 1, all right? So the probability has to sum to 1 of these occurring. The probability of any one of these 4 occurring, okay, head, 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 tail, head, head, tail, head, head, tail, head, head, tail, head, 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 is given by the probability of success cubed times the probability of a failure. We could compute those and add them up, and that would give us our probability. That's what this formula for the probability of X does. We're making 4 tosses. In order to get 3 successes, the probability of that is going to be the probability of a success cubed times the probability of a failure. If we relate that back to the original formula, N is 4, X is 3. We have probability of success cubed and probability of failure to the 4 minus 3 is 1 power. And if we pull up our binomial distribution tool, I guess I should show how I did that. Okay, so I got down to this binomial distribution tool, open it, and it will come up by default showing you a binomial distribution for 10 trials with a probability of success is 0.5. So let's alter this to our situation. We're doing 4 trials, and for us, the probability of a success is 0.8. That's the probability of a head. And we want to know what the probability is of getting 3 heads. Okay, and the tool just updates as we go. Notice up here, the particular test that I've selected is the probability that the number of successes that we get is exactly 3. I could also ask for less than or equal to 3, or greater than 3, or between some 2 values, but we are interested in the probability of it getting exactly 3 heads. And what we get is this value, approximately 0.4. Whoops. Let me pull up my, yeah, okay, so we've got 0.4096 is the approximate probability of getting 3 heads out of 4 tosses. Okay. Now, without doing any derivations here, the binomial distribution, like any probability distribution, has a mean and a variance and a standard deviation. And if you do the analysis, you discover that the mean number of successes, if you do n trials and the probability of success is p, the mean number of successes is simply n times p. So in our case, 4 times 0.8 would be 3.2. So the mean number of successes that we're going to get in 4 trials is 3.2. The variance is the sum over the possibilities of the number of successes that we want, or the value that we get, the number of successes that we get, minus the mean squared times the probability of that many successes. This, after a little bit of algebra, turns out to be NPQ, the number of trials times the probability of a success times the probability of a failure. And we just take the square root of that then in order to get the standard deviation for this distribution. Okay, so let's take a look at one application of this binomial distribution in a famous experiment called the lady tasting tea, which was described by, I don't think he was Sir yet, although maybe he was, Ronald Fisher, who was one of the very early, very influential statisticians. And he published this book called The Design of Experiments. He has been dead for a long time. You can go out to the web and you can find a PDF of this Design of Experiments book, and it's a very worthwhile read. Okay, so in this experiment, a lady claimed that if she were served a cup of tea made with milk, she could tell whether the milk was added to the cup followed by the tea, or whether the tea was added to the cup followed by the milk. Now, if you are a tea drinker, perhaps this makes total sense to you, and perhaps you can do the same thing. You can tell when you drink a cup of tea mixed with milk whether the tea was poured into the cup first, followed by the milk, or vice versa. As a Diet Mountain Dew drinker, I confess I have no idea about this particular experiment. Okay, so Fisher designed an experiment to test the claim that this lady made. Could she, in fact, tell the difference? Now, let's think about that question. Can she tell the difference? What are you willing to accept as proof that she can tell the difference or she can't tell the difference? She claims that she can tell the difference. Does that mean that you test her infinitely many times, and if she answers correctly infinitely many times, that she's correct and she can actually do it? Well, that's obviously pretty impractical. You know, we're not going to be able to test this lady infinitely many times. So how many tests can we do in order to get to a comfortable level of certainty that this lady is correct, that she can tell the difference, or not correct, that she can tell the difference? So let's prepare 8 cups of tea. 4 of these will have milk added first, and 4 will have tea added first. Now, we're not going to tell her, obviously, the order in which the ingredients were added for each of these cups. We're going to present her with these cups in some random order and will record whether she determined correctly or not. Now, if she is merely guessing, if she really can't do this, and consequently she's merely guessing on each of the cups, the probability of her being successful in telling whether the milk was added first or the tea was added first is 0.5. Okay, because half of our samples had milk added first, half of our samples had tea added first. If she's guessing, her probability of being successful is 0.5. Well, so if she is guessing, what is the probability that she gets at least 7 or possibly 8 correct? Let's check that out using ISLE. This is a binomial situation. This time we're doing 8 trials. Oh, and by the way, we are testing whether the number of successes is greater than 6. Okay, so we're doing 8 trials. The probability of a success is 0.5. And we are asking, oh, for some reason it reverted back to x equal to 6. I want x greater than 6. And the probability, if we give her these 8 cups of tea in a random order, and if she's guessing randomly, her chances is 0.5, then the probability that she's going to get 7 or 8 correct is remarkably tiny. It's only 3.5%. What does this mean? Okay, what it means is if she is guessing and she gets 7 correct or 8 correct, then she is remarkably lucky. Okay? So our hypothesis, if you will, we start out making the presumption that she is guessing. We know from the way that we've set up the experiment that the probability of her evaluating the tea correctly, if she's guessing, is only 0.5. Since she was able to get 7 or more right, there's only a 3.5% chance that she could do that if she is guessing. That, the experimenter believes, Fisher believes in this particular case, is a low enough probability that although it doesn't absolutely prove that she's not guessing, the probability that she's guessing is only 3.5%. And so it makes more sense to assume that, yes, she can actually do this. All right? Now, oh, by the way, apparently she actually got 8 correct, and the probability of doing that is obviously even smaller than 3.5%. Again, still not proof. Even if you get 8 correct, you can do that by luck, so it's still not proof, but it's very good evidence that she can, in fact, do this analysis. Okay, all right. So, so I have just gone through and answered this question here. What's the probability of her getting 7 or more right out of 8 trials? And we demonstrated using the ISLE widget with the binomial distribution, using ISLE with the binomial distribution widget to do that computation. Now, our next, we have some tests of understanding here. This first one relates to a trivia quiz that you haven't seen, so we're going to punt on that one. And instead, let's take a look at this Amazon problem. Amazon hopes to hire up to 6 MISM students and makes offers to 10 students. if the probability of a student accepting is 0.4, what is the probability of more than 6 students accepting the offers? Okay, so that's our first question. Well, this is a binomial distribution because either the student will accept the offer or will not accept the offer. We have 10 students, so our number of trials is 10. The probability of a given student accepting is 0.4, and we want to know what the probability is that more than 6 students will accept. We have our test corrected, our test selected correctly. We're asking for the probability that the number of students who accept is greater than 6. All right, and so the probability of that is about 5%. So that's a pretty low percentage chance that we get at least the 6, or that we get more than the 6 that we. All right, we're hoping to hire up to 6 MISM students. The chance that we overshoot and hire more than 6 is just a little over 5%. Now we're going to change the rules a little bit. Suppose 2 students quickly accept, and now what's the probability of more than 6 students accepting? Well, in this case, 2 students have already accepted. So the problem now changes to we have 8 students remaining. All right, so the number of trials has been reduced from 10 to 8 remaining. And what we want to know is what the probability among these 8 is of more than 4 accepting. Okay, the probability of a given student accepting is still 0.4. So, if 2 students accept immediately, we have 8 students left that we're waiting to hear from. 2 have accepted. So the question now is, what is the probability that more than 4 of these remaining 8 students will accept? And that's 0.17. So we have a bit higher probability of overshooting and getting more than 6 students than we had in the case where we had not yet heard from anybody. Alrighty, so that is the binomial distribution, and we took a look at using the binomial distribution tool within ISLE to compute probabilities. There's a couple more pages pertaining to the quiz experiment that we're going to skip over. All right.